Today I want to talk to you about type checking. But I want to start with a confession. If you're a programmer who's anything like me, your code is terrible, or at least it's not as good as you would like it to be. So code is full of errors. Here's an example in an Adobe enterprise system, and I've circled the java.lang.null pointer exception that you get when you try to use it. But it's not just websites that are a problem. It happens on phones, it happens on embedded devices, lots of other places where we don't want these sorts of errors to occur. So the fundamental problem here is that Java's type system is too weak. It's great, but it doesn't do enough for you. It prevents all sorts of boneheaded errors like assigning a string, hello, into an integer. But there's all sorts of code that you can run and that you can compile, will compile cleanly, and then it will fail at runtime. So here are 3 examples on this slide. Do people see why this code fails at runtime? How about for the first one? The console might be null. For instance, suppose you're running as an app. How about the second one? The empty list is immutable. Not all lists are, but the empty list is. And how about the third one? Yeah, this one's actually not going to throw an exception. It's much worse than that. It will fail to throw an exception and keep executing if you have a SQL injection attack. So the good news is that type systems can prevent all of these. If you're using the right type system, it will reject this code, and it'll only be able to run code that's actually correct. Type systems exist to handle null pointer exceptions, unwanted mutations, concurrency errors, and lots more. So this is a solved problem in theory. The difficulty is that it takes a long time to transition from theory into practice. We've seen the rate of releases of the Java language. So I want to tell you about a different way, a way we can leapfrog that. So when you're using a static type system, you run source code through the compiler, which does type checking. And if there are any errors, every error indicates a bug or you wrote the types incorrectly. So you fix those and change the source code. And eventually, you have no errors, so you get out an executable, and you can run it. And that's great. And what happens when you run it? It crashes. So here's a different approach. You still have the source code and the standard compiler and type checker, but you can run a pluggable type checker in addition. We have a tool for building these called the checker framework. It issues warnings. Every warning indicates there's a bug or you wrote an annotation wrong. And for example, if you have a variable myref that's marked as nullable, if you try to dereference that, you'll get a warning because it might fail with a null pointer exception at runtime. So eventually, you can always, this is optional. You don't have to run these if you don't want to. But eventually, if you have no warnings, you can then take the executable and run it, and you know that those particular errors will not happen at runtime. Furthermore, if there are other properties you care about, you can run as many of these as you like, as many or as few as you like, and you get even more guarantees. So we have this tool called the checker framework, which allows you to build pluggable type checkers. Essentially, you can think of it as plugging a new type checker into the Java compiler. You still use the Java type system, but you get to add more checks if you want them, where you want them. It uses JavaC's standard minus processor argument that's been in Java since Java 5, and there's also integration for tools like Ant, Maven, and Eclipse, and it's freely available. Here's how you write these the types for these pluggable type systems using Java's type annotations. Java will let you write annotations anywhere you write a type. So you can say, for instance, that a particular query string is untainted. It's not going to be a SQL injection. Or you can say this is a list, not just a list of strings, it's a list of non-null strings. Or after you've constructed some object, you could cast it and say it's not going to be changed anymore. The last declaration there is a better declaration of the JDK's built-in unmodifiable list. What you'd really like to say is not that it implements list of t, but that it implements read-only list of read-only t. You can read but can't modify the list, and you can read but not modify the elements in it. These new annotations on types are stored in the class file. They're handled by tools like JavaC and JavaDoc. And this is such a compelling use case that it's a built-in part of Java 8. But if you're using the checker framework, you can also use it today with Java 5 or 6 or 7 by just writing them in comments. And then you can remove the comment characters when you finally upgrade to Java 8. So there's no reason to delay. So I've told you a little bit about this notion of pluggable type systems that helps you eliminate certain types of errors. Now I want to talk about some case studies, and we'll also give you a demo of the tools in action. So we've run type checkers on over 3 million lines of real-world code, and they find real bugs. We found hundreds of user-visible bugs and lots more instances of internal errors or code smells. It's actually pretty easy to use. We only had to write, on average, 3 annotations per 1,000 lines of code. So way less than the cost of writing generic types, for example. Here are some examples of the programs that we've run it on. The approach we took with each of these was we would first write the annotations, then you run the compiler and you see what it says. Every warning you get either indicates there's a bug in your program or it indicates you've written the annotations incorrectly. So at that point you fix the problem and you rerun the compiler. Eventually, when there are no more warnings, you have a guarantee that certain errors won't happen at runtime. A certain specific error, not that your code is perfect in every respect. Let me give you some examples of type systems. So when you're thinking about a type system, there's 3 questions you want to ask yourself. What's the runtime behavior I want to prevent? What are the legal and illegal operations? And what are the types of data if I want to think about this? So let's think about preventing null pointer exceptions. That's something that a lot of people are interested in doing. We want to prevent null pointer exception. And what's the legal operations? If you're dereferencing, it should only be a non-null reference. You shouldn't try to dereference a null value. And then we can divide all the data in your program into 2 types. There are non-null references that are guaranteed not to be null, and there are nullable references that might be null or might not be null. We're not sure. And those 2 are related in a type hierarchy, which is exactly like the standard object-oriented type hierarchy that Java already uses. Like a string is a subtype of object. Similarly, non-null object is a subtype of nullable object. And then with that, the type checking just works in exactly the way you're accustomed to. Let me give you an example of some of the many bugs we found. Here, Google Collections has a class called forMapWithDefault. This is, it's a mapping, and if there's a key missing, then you can use the default value instead. And it has a hash code. Classes should have a hash code that returns the map.hashcode plus the default value.hashcode. And this throws a null pointer exception because the default value can be null, and the hashcode method doesn't look for that, doesn't check for that. So we found 9 crashes like this in Google Collections alone. And we found that despite the fact that it has 45,000 tests, and 2/3 of its lines of code are actually tests. And it was already using the findbugs nullable annotations, and findbugs ran cleanly on it, issuing no warnings. Now, you can't blame these people. The Google Collections authors have done a fantastic job. But you can't possibly write all the tests you need to write. It's much better to let a machine do that. No human can compete with that sort of thing. So a machine's a great way to complement all the tests that you've written. Let me give you an example of another type system that we use to find real bugs. This is one for Java signatures. So what's the runtime behavior you want to prevent? We don't want to suffer class not found exceptions at runtime. Java has a class.forName method, and that takes a so-called binary name. Turns out Java has 3 different representations for a class as a string. So we divide all data into 4 types. They're unqualified strings, sort of arbitrary strings like hello world. They're fully qualified names like package.outer.inner, binary names like package.outer$inner, and field descriptors like lpackage/outer$inner semicolon. And these are all used in different parts of the JDK and the JVM, and you'd better not mix them up, because if you do, bad things happen. Here's the hierarchy. We have unqualified strings at the top, and then we have these 3 other types, and they must be kept separate. It's actually quite important that they be kept separate, and no one is a subtype of the other. No one can be used where the others are supposed to be used. So here's an example of some of the bugs that we found. In the JDK, there's a class named class, JavaLine class, and it has a method forName. And if you read the Java doc, it takes as an argument a string, and the Java doc says that string is the fully qualified name of the desired class. So let's pass it a fully qualified name. You get a class not found exception. Because actually, it shouldn't be a fully qualified name. That's an error in the documentation. It has to be a binary name. If you pass it a fully qualified name that doesn't happen to be a binary name, then the system's not going to behave properly. And you'll never notice this until you actually have an inner class. If you don't have an inner class, you'll never notice this until one of your users starts to use it and then discovers the problem. So we found 11 crashing bugs in OpenJDK, and we found 13 more crashing bugs in libraries, where if you follow the documentation, your program's going to fail. Here's some example annotations we wrote. Class.forName takes a binary name as an argument. Class.getName returns a binary name. And class.getCanonicalName returns a fully qualified name. So if you were to write the code down at the bottom, where you call getCanonicalName, and then you try to call class.forName on it, which is something I've seen real code do, then the type checker will warn you. It will say, this is erroneous, and will cause you to rewrite it correctly.
Okay. So the next type system that we want to discuss is a regular expression type system. When you use the regular expression type utilities in Java, you can get two possible exceptions. You can get a pattern syntax exception if the string is malformed, and you can get an index out of bound exception if you access a capturing group that's not within the regular expression. So the legal operations that we want to distinguish are that pattern.compile is only called with a string where we know that the string is a regular expression. So you cannot use an arbitrary string, just regular expression strings. And for matcher.group, you have the additional constraint that you know the number of capturing groups. You cannot access a capturing group if you're not guaranteed that that capturing group exists within the string. So we do this using two qualifiers, the unqualified again to specify arbitrary strings like hello world, and regex for strings that are guaranteed to be regular expressions with a certain number of capturing groups. Here's some example source code. We get the regular expression from some user input and then call pattern.compile with it. If we do this with a malformed regular expression string given by the user, we can get the pattern syntax exception. We just don't have any control about the user input. On the other hand, the next step is that we compile the pattern into the matcher. It matches against that string, and then we try to access group number 4. We have no guarantee that group number 4 exists within this regular expression, and at runtime, we might get an index out of bounds exception. So this is very brief code and might look artificial to you. Let's look at a real-world demo of an application that uses regular expressions. So one of the case studies we did with regular expressions is this tool called JC, which is a distributed search engine. One of the features that it provides is a query within the tables that it has, and you can search for string ABC, and as this is a fresh installation, we don't find any tables, so we get the message, okay, there's nothing. But what happens if we enter a malformed regular expression? Nothing happens. We don't get an error message, we just get a blank table or a blank page. So what the server administrator can do is go into the server log, and only in the server log, he finds that there was an exception. And he finds, okay, there's an unclosed group here, and then he can start debugging, go into the source code, see where the first part of his code is, and he sees that he needs to go to table ymark line 65. So let's have a look at that code, and here we have that exact same pattern. You get the regular expression pattern from the post, so you get it from the user, and then he did some validation. He checked whether it's empty or just a regular expression that matches any string, and otherwise he just compiled the pattern. So and now this throws the pattern exception. So what we did is we set up a tool with this case study and compiled it with the regular expression checker. And the message that you get is exactly on this line. So you see that the call to pattern.compile gets as argument an arbitrary string, but pattern.compile is annotated to only take a regular expression string. So now let's have a look at how to fix this bug. The fix is quite simple. Instead of just always compiling it, we have to make sure that the string that the user provided actually is a regular expression string. Only if it's a regular expression string, we compile it, and then if it's not a regular expression, we output some readable error message. So let's see whether this type checks now. So we stop JC and we compile it. And now we don't get any error message anymore. So this passes the regular expression checker, so we can be certain that now we don't have any exceptions, regular pattern syntax exceptions in this application anymore. Just a second. Now it's done, and we restart JC and can go back to the web page. And let's reload that table. Now, if we insert an invalid regular expression, the user gets an error message. So by using the regular expression checker, the programmer was pointed directly to the line of code where he needed to do something and could make the user experience a lot better. So instead of the server administrator going to the log, you get immediate feedback about what's going wrong. So the JC developers were so excited about the feedback that we gave them. We gave them a total of 35 bug reports, that they decided to integrate these annotations into their source code and use it in the development process. So in the search engine, you have a lot of regular expressions, so they were very happy about this feedback. Cool. So what we've seen so far is what is pluggable type systems and how can the checker framework help. And we've given you 3 examples: the nullness checker, the signature checker, and the regular expression checker. What we want to do next is brainstorming with you about ideas how you could apply this, this tool for your problems. So for this, we have 3 questions that we want you to ask yourself. What is the runtime behavior that you wish to prevent? What are the operations that should be legal or illegal? And what types of data are there? Do we have?
So if anybody has an example of some runtime error or any other behavior that you'd like to prevent, we just want to take those suggestions and we'll put them up here on some slides. Yeah, right there.
You may have done this already, but something like find bugs guarded by.
Okay, great. So the suggestion is that we want to prevent. So what's the exception that you want to prevent? So this is essentially a locking, a concurrency type system. What's
right. So it wouldn't be an exception per se. It would be it might be a silent
Mm-hmm.
exception at runtime, but the problem being that you're accessing something that should be always guarded by a mutex, but you're accessing it without first obtaining a lock on the mutex.
Yeah, that's exactly right. So the problem is that you have a lock and you have some data, and you should only access the data if you're holding the lock. And if you access the data without holding the lock, then you can have race conditions, you can have other terrible things happen. You can get concurrency errors. So essentially, we're trying to prevent these race conditions. So the legal operations are, you can access data if and only if you're already holding the lock for it. And then what are the types of data? So how would we express a data property about the things we care about? Essentially, you started out with that by saying you wanted to have this guarded by annotation. So it essentially says, here's a datum, and here's the lock that represents it. Now for every datum, I know which lock represents it. So this is a great example, and it's one that is distributed with the checker framework. So if you download our tools, you can already use this today. So fantastic. Other suggestions? Yeah.
So variation of that idea, if I want to do only immutable operations, concurrently, like on a parallel collection, and there I just want the, I guess now, and
Yeah, so that's another great example. The idea is we want an immutability type system. We want to have a guarantee that certain data are not side affected. So some in your program, some lists fine to mutate. Other lists you shouldn't be mutating. So the legal operations are you can mutate mutable data, you can side effect mutable data, but you should never side effect immutable data. So we're going to divide all the data in your program into either 2 or 3 types, depending on how sophisticated you want your type system to be. There's immutable data that may never be changed. There's mutable data that anyone can change. And then you can actually refine this, which is desirable in some circumstances. For example, to have data that this reference can't change, but that some aliasing reference could change, and that's read-only.
Well, there's a temporal dimension, right? It's that within this particular block, I don't want the mutation.
Right. So the read-only can express that. So, for instance, if you have suppose you have you're holding some data, you're allowed to mutate it. You want to pass it to another routine. That routine has no right to mutate your data. If that routine has its parameter annotated as read-only, you have a guarantee that during the execution of that routine will not mutate your data. But once it's back, you still have every right to mutate your data. And that's different than something that's completely immutable and can't be changed by you or by anyone else.
I guess the difficulty that I have is that it's being captured automatically.
So you said it's being captured automatically?
It's being captured by closure.
Oh, okay, so you're saying...
The closure, yes, does translate into something with a constructor, but I'm not actually writing that constructor.
Okay, so the notion of writing a closure that's going to capture data outside it is a separate one, and that can be handled as well, but I wasn't talking about that in my example. It's a good point. And and that's one of it's subtleties like that are why you want to use a real type system. You don't want to use something like find bugs, which helps you find, sorry, that's incorrect. You do want to use something like find bugs, it's useful. But if you want to find every problem, you want to use something beyond the heuristics as well. So great example. Other brainstorming, other examples of things that people run into. Yeah, and they're in the back. A class cast exception? Okay, so what we want to do is have a guarantee that you won't suffer this exception at runtime. So what are the operations that you want to permit, or what are the operations you want to forbid at compile time?
Casts. Sorry.
Yeah. Sorry. Yeah, class cast exception. Sorry. Right. So the Java type system already lets you do some of this because the compiler can tell you this cast is guaranteed to succeed, this cast is guaranteed to fail, and some of them do that, some of them don't. But you could actually you could write a pluggable type checker that would do those things even if your compiler doesn't, and will also track more finely than the Java type system can what types something is. So for instance, suppose you have a variable that's of type object and you put a string into it. Now if you cast it down to string, you know that's going to succeed. Java doesn't know that's going to succeed. But it turns out that our type systems have a feature called, so the academics like to call it flow-sensitive type refinement, but you can think of it as do what I mean. That means it knows what type the thing is even more finely than the Java type system, even if you haven't redeclared it, even if it's the same variable. So that's a good example. There, and then, was someone raising a hand over on the corner? No? Okay, and then I'll get you next. So.
Required parameters on method call.
Okay, required parameters. So are you thinking of something related to var-args? Because, Java makes you supply all the parameters.
Well, you can
on the command line of the program.
No, like when you call a method, you can specify, you have certain parameters you can say null. So basically making sure that certain parameters you get are required.
Okay, right. So the example here is, suppose we have a method that takes a bunch of parameters, and we want to make sure that some of those parameters are definitely not 0 or definitely not null. or definitely not an empty list.
Or constrained to a certain
Yeah.
range. Or
So those are all great type systems, and our null pointer type system will already handle this. If you just mark the parameters at the method declaration as being non-null, then anytime you try to call it, if the type system can't guarantee that value is non-null, it will issue a warning. It'll warn you that there may be a problem. And you can do the same thing with non-zero or with non-empty lists or whatever other constraint you'd like to express.
A variation on that theme would be the builder pattern, where you have to call a series of methods and then you tell it to construct, but you want to make sure you call at least the required ones.
Okay, so here the idea is that what we'd like to do is call a constructor and then have an object. Sometimes life is not that simple. What you need to do is call a constructor, then call a couple more methods, and now you finally have the fully constructed object. So there's a concept called type state, where when you make a method call, something can transition in type. Like you might have files, and files are either open or closed. And when you call file.open, it changes from being closed to being open. And you're only allowed to call write or read on it if it's actually open, not on every file. So you could do exactly that same sort of thing. This gentleman here.
I have annotation still parameter which is nil to be labeled as.
Okay, so here's an example of a restriction on data. So you can think of all the strings in the world, but you would like some variables to only have a string that's the name of a method, or it's always a zip code, or it's always a validated credit card number, or something like that. So you can do the same thing. You can say, I have an annotation that says this is any string at all, and then I have a different annotation that says this is definitely a method name, or this is definitely a zip code, or it's definitely a credit card number, or it's definitely a regular expression. It turns out that that's very much like our regular expression type system, because there are all the strings in the world, and then there are those that obey some certain formatting property. So I didn't go through our methodology, right? We have a methodology. We asked 3 questions, and I got so excited I didn't go through the methodology. Don't do that. We've got some data that has some particular format. The legal operations are you're going to have methods that are annotated to take only a method name or only a zip code. And the types of data are either data has that particular property, and it could be non-null or it could be non-zero. I mean, these are really just different ways of expressing the same concept. Though, of course, they're useful in completely different ways in your program. Good. Yes? Right. So I don't know if people could hear that, but essentially it was you'd like to say that certain method calls will change the state of the object, like changing a closed file to an open file, or changing an empty list to a non-empty list. And this is essentially a type state. Yeah, exactly. Thank you very much. So Werner's already got it all up there. Let me see how the time is. Let's take at least one more. There was. Did you have one over there?
Yeah, I was going to mention leaks caused by not closing resources.
Right. So you could actually put that in the. So sorry to repeat the comment. What about having a guarantee that you close your resources? Because if you don't close them, you might have a leak. And that could be a performance problem. It could even be a security problem. And you can put that in, you can express that in a similar way in a type state system by saying, by the time I exit the routine, I want the file to be in this particular state, like it to be in the closed state. If control flow is complicated enough, this turns out to be more difficult to express. Good. So this, yeah. So a concurrent modification exception. So you could actually fit that into our existing immutability type systems. So essentially that will say, this thing shouldn't be changed during this scope. And so the idea is, if you're iterating over some list or other collection, if you modify it during the iteration, you're going to get a concurrent modification exception, whether that's in multi-threaded program or a single-threaded program. Yeah. So these are great examples. and there are actually a ton more that Werner will tell us about.
I always enjoy this brainstorming part a lot because it's always great to hear new ideas. So with the checker framework, do you hear me?
Can people?
With the checker framework, we deliver a bunch of different type systems, some of which that you already mentioned. So we have a tainting type system that tracks taint, which we need for SQL injection attacks and things like that. We described the signature checker already. Null dereferences is one of the big problems in object-oriented programming, and I think it's very important to use a type system like that. Concurrency came up as one of the problems that we definitely want to handle. Mutability and side effects is a very common problem. You want to be sure that certain data doesn't get modified. Fake enumerations for legacy code is quite interesting, where you have integer constants, and you basically don't have any guarantee what the range for that constant is. You can introduce your own data type and say that only these 3 different values are valid for this parameter. You don't lose any performance. It's still a primitive type, but you have the additional static guarantees about your type system through the type system. Internationalization has the cool property that the type system looks into an external file and looks up whether the internationalization key appears in that external file. So with your type checkers, you can do many things. You can look into external databases, see whether the user ID is in the database, things like that. Regular expressions we explained, and there are a few, from the research side, we have a few more extended type systems. So the final part of our presentation is how to build your own type system. In this part, we want to discuss an encryption type system. This type system is very simple, and we want to prevent that unencrypted data goes through the network. So we have the distinction between encrypted strings and unencrypted strings, and the send operation should only be called with encrypted strings as arguments. The type hierarchy for this is quite simple. We have the unqualified string, which can be arbitrary again, and the encrypted strings, which is a subtype. And you cannot pass an arbitrary string when an encrypted string is required. So the code that we want to type check is the send operation that takes an encrypted string. If you pass an encrypted string, the compiler doesn't warn you about it. But if you pass an arbitrary string and you don't have a static guarantee that the string was encrypted, you get a warning. The complete type checker for this is just 4 lines of code. We declare the annotation type at encrypted. We tell the checker framework that it's a type qualifier, and we tell it the subtype relation to the unqualified string. And then we also express to Java what the syntactic locations for the annotation are. So it's that simple to write your own type checker and just make the basic distinction between 2 different separate sets of types. There are basically 3 parts for a type checker. The first part is what we just saw, the type qualifiers. What is the separation of data that you want in your system? The second part is the qualifier introduction rules that tell you for each expression what should the qualifier for this expression be. So if you see a string literal in your program, how do you decide whether it's an encrypted string or an arbitrary string? And the third part are the type rules, which decide what is a legal program and what is a forbidden program. Let's have a quick look at each of them. So we've just seen that to declare the type qualifiers and the hierarchy, we do this purely declaratively. We have the annotation type, and using meta annotations, we declare that it's a type qualifier and what the hierarchy between the different qualifiers is. Then to declare the implicit qualifiers, we also use a declarative approach. We say that with the particular qualifier, so here we say for the nullable qualifier, it should apply to whenever the null literal appears in your program, you should use the @nullable type. And we also have other fields in that annotation. So for example, whenever you see Java-lang void, void is always a nullable type. So you can very fine-grained specify for each expression in your program what should be the default annotation. And the third part is the type rules. The checker framework provides the basic implementation for this, which basically just provides the subtyping checking for your qualifier hierarchy. So once you have the qualifier hierarchy, it just gets propagated through method calls, through field assignments, ensuring that this subtyping relationship always holds at runtime. And if you need to, you can customize it. So for the nullness checker, if you have a field access x.f, you need to make sure that the receiver x is non-null. And here's the code to do this. In the type visitor, you override the visit member select, which is the method that handles this, and you additionally ensure that the receiver has a non-null annotation, and if not, you raise an error from the compiler. So this is very flexible, very easy to do the declarative part, and all the power from the imperative part. Previously, we've seen the signature checker. So the signature checker that separates these different class name representations. And actually, most of the logic for this checker is implemented declaratively in the qualifiers. So we say that these are all the different string representations, and using declarative annotations, we can say what strings fall into which category of which annotations. So most of the logic for this checker is nicely encapsulated declaratively with the particular annotations. And that's...
Okay, so what you've just seen is that it's really easy to do simple things. I mean, here's the whole type checker for the signature strings that found those dozen errors in the JDK. It's also possible to write sophisticated type checkers. So for instance, the nullness checker, it turns out it's actually tracking 3 different varieties of properties at the same time. One is a property of whether a particular reference is null or not. Another is whether each object is initialized or not. And another is, for each map, what are the keys that are absolutely known to already be in it. That helps it to infer whether a particular call to map.get can be guaranteed to return non-null. So the checker framework has a number of very powerful analyses built into it that every type checker built on it gets to inherit for free. I'm just going to give you one example, which is you can think of it as local type inference or as flow-sensitive type inference, flow-sensitive type refinement. So here I have a variable x, and it's declared to be possibly null. And now I have 2 calls to x.toString. Same variable, same type. You'd think that they might behave the same way, but they shouldn't. The first one, you should get a warning about because it might throw a null pointer exception. The second one is guaranteed to be safe because it's inside a test. So our system is able to change without the user having to do anything, the type of a variable from line to line in a sound way, so it doesn't miss any warnings, but it greatly reduces the annotation burden. So this is one among several features of the checker framework that let you write less code, that let you write fewer annotations and make it easier to use.
Is it able to decode like that check if that was an and or an or?
Yes, so it also handles ands and ors and try and finally and whatever type of control flow you want to write. It would, yes, if an or would let the null slip by, it would catch it. And if x is not equal to null and x.toString.length is greater than 5, it wouldn't complain about that either. Because even though it's in the conditional, it's only going to get executed if x is known to be non-null. Good question. There's some other tools that are packaged up along with the checker framework. There are whole program type inference tools where you put a program in and it'll give it back to you annotated. We have tools that will take annotations and insert them into source code for you. We have annotated versions of the JDK for each of these type systems. So what we've told you about is this approach is one valuable approach to increasing the quality of your code. It's called pluggable type checking, and the checker framework is a way to build this. It's a powerful framework that lets you build these pluggable type checkers. It comes with over a dozen built-in checkers that you can use out of the box, and case studies have shown they found many latent bugs in real-world programs. But if you don't like those type checkers, or if you need some other specific property for your project, then it's easy enough for you to go ahead and write your own type checker, because that's another thing the checker framework does. And we taught you how to think about type systems. Type systems are not scary. It turns out that they're simple. If you know how to ask 3 simple questions, what's the behavior that you want to forbid? What operations are legal? And what are the types of data? So now I encourage you, go out, download this, try it, improve your code, and give us feedback. And we have some time, so we'd be delighted to answer questions that people might have. Yeah.
So you showed us how you can sort of write certain simple checkers declaratively.
Mm-hmm.
But if you really want to get down into the guts and sort of deal with something more complicated, is there a way to extend the code that you guys have written which processes those declarative annotations?
Right. So the question is, we've shown you a bunch of declarative. We've shown you how to write simple type checkers declaratively. So if you want to do, and it turns out you can do fairly rich things declaratively, but as you get to more and more interesting type systems or more and more special cases, then you're going to want to write procedural code. And almost all of our type checkers actually come with some are written declaratively as much as we can, and then have procedural code. So it turns out that if you want to do interesting stuff, declarative isn't going to hack it. But declarative is a great way to get started, and it greatly reduces the amount of code. So all of this stuff can be overridden procedurally. Does that answer the question?
Yeah. Are there any tutorials or documentation on how one goes about doing that?
Yes. So we have a 100-page user manual. Most of that is just sort of 5-page manuals about each of the type checkers, but we have several chapters at the end about how to write your own type checker as well. Question? So the question was, what type of license is it distributed under? I think it's GPL, which means you can use it however you want, including internally at your company.
So I was thinking of another property that I'd like to check. Sometimes when you design a framework, you want to force someone to override a method and then call the superclass method.
Mm-hmm.
And they can't bypass that call. And I didn't quite see what's the data that's involved.
Okay, so the question is, here's a property I want about my code. I want to make sure that everyone who overrides this class definitely redefines this method, because I don't want them to use the default implementation. That's a property about the...
I wanted to call my superclass.
Right, so and they have to call the superclass. Oh, if they do override it, they have to call the superclass. Okay, right, they might not override it, but if they do, they better call the superclass. So that is not a property of data of your code. That is a property of the structure of the source. So the checker framework is excellent for anything that you can express in terms of your data. You could write a checker that would do exactly that using the checker framework, and people have. But there, you're not using its entire power. You're just using it to get access to the AST and then doing pattern matching against the AST. So it's not good for all problems. It's not good for all quality problems. Yeah?
Can you run the checker on existing legacy code or third-party app? Do you need to modify the source code for those before you run it? Or?
So you can run these on existing legacy code. If you have no source code, you can write annotations in a separate file if there's some library that it uses. You need to change the source code to add the annotations. You do not need to make any other changes to the source code, except that as soon as you start running the checker, you're probably going to find bugs that will make you want to change the source code. If you already understand the design of your legacy code, it's pretty easy to write the annotations. You sort of know which strings are addresses and which strings are social security numbers and which variables are supposed to be null. If you don't understand the structure of your legacy code, then you're in for a reverse engineering nightmare, after which you can spend just a couple moments typing up what you learned and putting it in the source code as documentation that won't decay because it'll be automatically checked. Yeah.
So on the previous page, you showed some Pluggable you showed inferring that text works to check files. Can you, if you've got a utility method which validates programs, can you use that as a
Great question. So here, I've shown you something that looks kind of magic. It's built into the nullness checker that it understands x not equal to null and what that means. The question is, I have a utility routine that validates my SQL or that something is an address or that kind of thing. And the answer is yes. You can annotate that saying, please utilize that for this flow-sensitive type refinement in exactly the same way as the built-in stuff. So that is possible. And we do that in our checkers. Yes?
As we see in this example again, do you actually need the null check for the second dereference? Or would it suffice to know it has been dereferenced?
Yeah, so Stefan is entirely correct that in this particular example, if you call x.toString twice in a row, you know the second one's never going to fail. Either the first one fails or there's no failure. So I could have put these in the other order if I'd chosen. But yes, thank you. Yes?
Is there any consideration of extending the checker framework so that it can work with Eclipse? And the reason I ask is because, as I understand it, you don't issue errors, you just issue warnings. And so for a developer in Eclipse, you see your warnings inside of Eclipse, but this would not include any checker framework warnings. Later on, you might run Maven to compile, but the output of Maven is verbose enough that one might not be looking for warnings there.
Okay, so the question is about integration with external tools. And the concern is that why are you just issuing warnings? Why aren't you issuing errors? These are all serious things. I mean, so we have some developers who say to us, I'm glad they're warnings because that means I can, go back and actually, occasionally I want to run an experiment and actually just run the code before I get all the types perfect. And other people say, this is so serious that I never want to run my code unless it's all perfect. And so the fact that it's warnings will support both of those. I think it's possible to convert the warnings into errors if you like. So there is a switch that will turn all of our warnings into errors. And you could choose to use that.
Well, his question was, can I see him in Eclipse?
So the question about integration with Eclipse? Okay, so if you look at our underlying implementation, it's integrated with Java-C. And so it's essentially using Java-C's ASTs. Eclipse has a different compiler. And so if, and that's unfortunate. It's a great compiler. It's unfortunate that it's different. So what our Eclipse plugin does is it actually runs Java-C under the hood and then exposes those back as Eclipse warnings. And our Eclipse plugin is, mostly functional. We've had people report that they're having good success with it. We occasionally get a bug report. Let us know how it works for you. Yes?
Does the Eclipse plugin support incremental?
Does the plugin support incremental build? I don't think so because it's calling out to Java-C. I'd have to check. Yes? I'm sorry? Okay, so the question is, which Java version does this work with? And the answer is it works with any Java version. So this idea is so compelling that Java 8 has special syntax to support this tool. Java 8's not coming out for a little while yet, but you can write them in comments. And now you can compile with any version of Java. Your coworkers won't be disturbed by it, but you can have this extra checking if you use the Java-C that's shipped with the checker framework. Does that answer your question? Yes?
Would some of these type checks be incorporated in the language?
So that's a great question. So, wow, this is such a fantastic idea. Why don't we just put this into Java itself? Why is this an external tool at all? And there are a couple reasons for this. One is that not everybody wants it. Another is that because this is a library, that means everyone can experiment with new type checkers. There's actually, especially in terms of things like immutability, there's no consensus in the research community about exactly what is the precise single best and perfect type system that everyone should use. So this actually just allows more flexibility. There is a JSR that's now dormant, JSR 305, that wanted to standardize some of this. And hopefully maybe in a future version of Java, some of them can be standardized. I do not believe they should all be standardized because different people need different things. Okay, well, you're a fantastic audience. This was a lot of fun. We're around. Please ask us more questions and go out and make your code better. Thanks.